Okay, so today we will be studying on real and reactive power scheduling, but today we'll start just an introduction to real and reactive power scheduling. Okay, so last class we have learned about how to control the power flow. Okay, there are different ways or techniques which we can control the power flow. Okay, so we can use TCR and we can use step changing transformer, or we call it as a phase shifting transformer, and then AC to DC, DC to AC conversion, and then we can control the power flow. Okay, so today what we will do is we'll see the real and reactive power scheduling, how to schedule real and reactive power, just an introduction. Okay, so next class we'll see the real, how to schedule, but today we'll see introduction, like what is mean by scheduling. When somebody said scheduling, what do we understand by scheduling in the uh, power system? Okay, so what is mean by scheduling in power system? But our objective here is these three objectives we have to do. In this lecture you will learn the following. First is what is mean by scheduling. Okay, before we schedule the real and reactive power, we have to know what is mean by scheduling. Okay, and the example of control variables and constraint. So to schedule we need control variable and constraint. So what are the control variable and constraint in power system? What with example we'll see that. Then towards the end we'll see objective functions. Actually, so when we start about the real and reactive power scheduling, we are going towards the optimization, and then detail optimization we will learn in the seventh semester. Okay, definitely we'll learn in seventh semester, and hope I will be take or continue this optimization. Actually, it is optimization in the seventh semester, but this semester and then in this unit we will go through what is scheduling, and then when we study about the scheduling we are going a little bit towards the optimization, and then basic of optimization we learn here, but this will be continued in the seventh semester. So to do a optimization we need this all control variables, constraint, objective functions. So based on that we have to do a optimization. Or okay, so these we will learn in seventh semester, but introduction to optimization we will carry it out in this module in unit 5. Okay, so first let's see what is meant by scheduling, control and scheduling. So in our previous lecture, okay, so earlier what we have learned is we have seen how to control the various quantity like, okay, voltage, frequency and power flow in a power system network. How to control the various quantities, like how to control the voltage, frequency of a system and power flow. We have learned in the earlier or previous lecture. Okay, so how to control? Then we use a frequency control example, speed governor, AGC, voltage and power flow regulator. Normally, these all are, we call it as automatic feedback controller, okay, which will work without manual intervention. Which means this speed governor, AGC, voltage and power flow regulator are essentially it is a automatic feedback, right? So it will give if there is some error, then based on this it will adjust and control our power flow or frequency or voltage, right? And then what it will do is it will ensure that these all quantities, voltage, power, frequency, within will be maintained within the acceptable range, right? So, but okay, this is regarding the speed control and AGC, what it perform, right? It's a automatic feedback control, and then it will without the manual intervention, but it will try to maintain these all quantities like voltage, frequency, power flow within the acceptable range. But this automatic controller, speed governor, AGC and other voltage and power flow regulators, what we need is we have to set some set point. Okay, you have to know that we have to make some set point, means reference point. Most automatic controller ensure that this quantity are regulated, which means voltage and but these value are maintained at certain set point, which means why we are saying 50 hertz frequency, we have set this reference, right? And why we are saying single phase for uh, why we are saying 400 volt for three phase, this has been set by set as a reference point, right? Just to keep within that range, we have set that point. Who is setting that set point is a operator. Okay, so this set point is reference value which is given to this controller by the operator. So we have to know that here is speed governor, AGC, and then all are the automatic feedback controller. Okay, so but in that automatic feedback controller, what we did is we have to set one reference point that is known as a set point. Who is setting that set point? Set point automatically it will not set. We are giving that set point by operator, which means 50 hertz. We are setting 50 hertz, 400 volt, 400 volt, or 230 volt. 230 volt is set by the operator, right? And then operator will again set that plus one. So based on that, this automatic controller will function. Means if it goes beyond that set point, then it will control by the automatic controller because it is giving feedback that it's going beyond the set point or over the set point. Okay, so this is actually set by the operator, and there exists some flexibility in deciding the exact value of set point. So now, okay, excuse me, there is automatic controller. Control with automatically, right, without manual intervention. But how? We have to set some set point. Who is setting set point? Set point by the operator. So now if I am the operator, if I set a wrong set point, this automatic controller will function as per that only. Okay, so there is some flexibility, okay, in deciding exact value of set point. So I say 50 hertz is a exact value, or 1 per unit voltage is a set point. But some operator may say that 1.02 will be also be fine per unit for voltage. Okay, so there is some flexibility. But if you set the 1.01 or 1.05 per unit, it should not go beyond the certain range, which is dictated by the certain curve, which we have learned earlier, like generator capability curve. Okay, so which we will see that. And then, but before defining about the scheduling, so now let's consider following example. Okay, there are 3 examples there, just I have given. So now our nominal value is 1 per unit voltage, let's say. Then plan operator may increase the value of this voltage setting of automatic voltage regulator from 1 per unit to say 1.02 per unit. Okay, this can be set by the operator because this is a set point, but this will increase the reactive power output of the generator. So what it will happen is when you set this 1.01 to 1.02 per unit, what it will happen is in our system reactive power generation output will of the generator will increase. Okay, how to control we have learned, but it will increase if you do like this. And we have to know that 1 per unit is a nominal value of a terminal voltage. Since every is accepted that 1 is a nominal value, but we can go beyond nominal value and then set 1.02 by the operator. Okay, it is not compulsory that we have to set the 1.0. Okay, so it can be set 1.02 and then operator may change it to value near about its, as long as it does not violate any limit. Okay, so see the capability of generator curve, which means 1.01 is a nominal value and then it is not compulsory. If you can set it is okay, but operator has a flexibility to set to 1.02. Okay, can set to 1.02 or near about this one, or which means 50 hertz. So that's why we are accepting 49.5 hertz. We can say that it's okay. Or 50.5 hertz also we accept, right? But here it has been given in terms of voltage. But when you set this, it should not violate any limit. So if you see the generator capability curve, you will see that if you cross beyond that, let's say, if you set to 1.02, and if you cross beyond that generator capability curve, there is certain limit which it will function. If you cross, then it cannot work. But if it is within that limit, then we can set. Okay, so that is one example. Then another one is, if you suddenly increase the load, what it has to do is your speed will decrease, which means frequency will decrease. But when you decrease, this governor has to respond, right, and try to restore frequency by increasing the generated power. We know that when sudden load increase, so speed will decrease, which means frequency is decreasing. When it decreases, this governor we have governor has to respond and try to restore frequency back to the required one, right? But by increasing the generator power, then subsequently what we do is, if we use AGC, then tie line power flow can be brought back to the nominal value. Okay, it will frequency, it will be controlled by governor. At the same time, this AGC will also control the frequency, means it will exactly bring to the nominal value, but governor will bring it to the range, acceptable range, and then AGC will bring back to the nominal value 50 hertz exactly. At the same time, if there is a tie line, power flow will also be regulated and then bring back to the nominal one, AGC. But however, our system operator may wish to alter the sharing among generators, say to decrease overall cost of the generation. So now there is a flexibility for the operator or system operator to alter the sharing among various generator, when to generate, and depending upon. So this operator we see, if you generate all generation from the all generator, or if all generator in the function, your cost might be very high. So now if two generators is sufficient, he may shut down another one or two generator, and then see from where it is a cheaper and then overall cost. Okay, this is another example, which means operator has a flexibility. And third one is, if due to line tripping, a system is alert or insecure state. So there are 5 states in power system, right? If there is line tripping and then system is in the alert or insecure state, then system operator may reduce the power flow through certain lines by changing the power output of different generator, right? So system operator has a certain flexibility. So this manual control action by system or a plant operator, which will essentially change this set point of various automatic controller, is termed as scheduling. Okay, so what is mean by scheduling? So now we have seen that, which means manually we'll control certain reference value or a set point, which is used in automatic controller like governor, AGC, by the operator, system operator, or a plant operator, is known as scheduling. Okay, so you have to know that what is mean by scheduling. Scheduling is actually this a manual control action by our system operator or a plant operator, which will change the set point. So just now voltage we have said example 1 per unit is a nominal value, and the operator has a flexibility to change to 1.02 per unit. This depend on, it has to be within the limit, which will be determined by the generator capability curve. And then this manual setting, which is used in the automatic controller, is known as scheduling or scheduling. Some call it as a scheduling, some call it as a scheduling. And then this scheduling or scheduling may be done in order to achieve a certain economic objectives. Why we are doing this scheduling? Why we are not keeping one per unit voltage? This is depending upon the operator, and then certain objectives are there, where if you do keep it at one, or ideal case, sometimes whenever you keep an ideal case, you may not achieve economy. So to achieve a certain economy, so we schedule such a way that, okay, so mean done in order to achieve a certain economic objective, or may supplement the existing or automatic controller action in ensuring system operation. Okay, so this is known as scheduling. Okay, so now when you do a scheduling, so before we do a scheduling, you know the definition of scheduling. So before we do a scheduling, we have to know what are the control variables which we can control. Okay, so a system or a plant operator has a flexibility to set several variables. Okay, not only the generator in order to meet certain objectives, but what are the control variables in power system? There are basically 9 control variables. Okay, so tentative listing of such variables are: first is real power output of generator, which are online, which means we can also control the real power output of a generator. How we will control is, this is done by changing the load reference, which means we are setting the set point for a load reference of the prime mover controls, and it's known as scheduling. Or when we change the load reference, we call it as a tertiary control, and primary, that is a governor, and secondary is AGC setting. Okay, which means so real power output of a generator can also be under the control variable by changing the load reference point, and that is known as tertiary control or scheduling. Okay, so tertiary control which can be set by the operator. One thing. Then another control variable is decision of whether to engage a generator at what time and for how long. Which means if there are 4 generators, how much generator can be put in operation and how long, okay, and at what time. Okay, so all 4 generator may not be used at once, may not be required to use one. Sometimes only 2 generator may have to use. So then at what time this 2 generator has to be on, and then for how long it has to be on. So this is also a control variable, and this is called as unit commitment. Means each unit how much you want to generate. Okay, unit commitment problem. Also this will depend on operator. So operator has to shut down 2 generator, and then 2 has to put in operation for 3 hours. Then another 2 hours all 4 has to on. This is known as unit commitment. Then another one is reactive power output of the generator, which is obtained by changing the voltage references of the automatic voltage regulation. Okay, so then another control variable. Other one control variable is tap setting of a transformer. You change the tap setting, then phase shifting setting of a phase shifting transformer. You shift that and control the output, right? Then another one is circuit breaker position for switching in or out shunt reactors or capacitors. So now whenever you require a reactor, you have to put on this, and then whenever you are not required, you have to put off. So then it will depend on the circuit breaker position, and then also circuit breaker position for bypass or insertion of series capacitor in the transmission line. Then HVDC power flow, which we have learned, okay, link and then reference of static bar compensator and other power electronic control devices. Okay, so these are the control variables in power system. Tentatively I have listed 9. Okay, so actually these are the basic main, okay, so which are the control variables. Okay, and then these control variable, we are saying control variable because this control variable value can be set by the operator. Okay, but operator should not set it blindly based on our cost, and then all we have to see that. But we have to know that here this control variable will be set by the operator based on certain objectives to be fulfilled. If you want to fulfill economy, then we have to change all 9 control variable, or sometimes we have to change only 1 control variable, or sometimes we have to change 4 or 5 control variable, so that we have to see certain objectives. So later on when you do our optimization, we will know how to do this. And this all variable we shall call them control variable, means variables have limits, some of them on discrete value while others can be varied continuous. Okay, so even we said that these all are the control variables, 9 control variables. These can be controlled and they vary, but it has a certain limit. Example, voltage, it has to within the generator capability curve. All we have to know that there is a certain level, and then this freedom to set all control variable may not be there in the hands of one system operator. Okay, just I'm sharing here freedom to set all these control variable, which means 9 control variable are there. There may not have a freedom to set all these control variable by a single system operator, but maybe in the hands of many operator. Okay, so example in Bhutan, DGPC will do this whole thing, right? DGPC can also do a real power output of a generator, and then decision of this can also be done by DGPC. Reactive power also may be done. Type setting transformer, it might be done. Or if it comes to the circuit breaker position and a circuit breaker position bypass of insertion of series capacitor in transmission line and static bar HVDC power flow, in such case our BPC may do this, which means all these control variable, one system operator may not have a freedom to change this all. Okay, so which means it has to depend on different entities. Okay, so just I have given an example. So now when you change the control variable, we have to see that. Okay, so we cannot change the control variable blindly. Okay, so that's why your nominal voltage is 1 per unit and you cannot change to 10 per unit or 0.5 per unit. There should be a certain limit, constraint should be there. So that's why constraint on system operation. While an operator has a flexibility to set some or all the control variables stated above, okay, in previous slide. So when you change this, it has to be done with utmost care so as to not violate any constraint. Basically, there are 8 constraints which it has been listed here. So when you change the control variable, so we have to think of this 8 constraint of a power system. It should not violate any constraint. Okay, so when you set, so that's why 1 per unit, if you set to 1.02 per unit, it will be within this constraint. Okay, so that's why it is acceptable. But if you go directly to 0.1 per unit, so it may violate one of the constraint here, and then that's why it is not acceptable. Okay, so now you can see that some constraints are given below. That first one is Kirchhoff's voltage and current law should be satisfied. Okay, one constraint is, you know, that basic law for a power or a electrical engineering is Kirchhoff's voltage and current law. Wherever you try to solve a circuit, you use either current or voltage law, right? This has to be satisfied. What is Kirchhoff's voltage law? You know that. And what is current law? You know Kirchhoff's current law, KCL and KVL. It has to satisfy that first one. Then second constraint is, when you change that control variable, load or losses and generation should match at a nearly nominal frequency. If load is more and generation is less, again it is not matching, right? At nominal frequency, that too at the nominal frequency, means near about nominal frequency, 50 hertz. And losses or load and generation should meet this. Okay. Then another one is voltages as a bus or along a transmission line should be within the limits. Which means when you change this control variable, is voltage at the bus or transmission line should be within the limits. So every device has its limit, right? Plus minus. So it has to be within that limit. It's also one constraint. Then transmission line should be loaded below their thermal limit. It should not be loaded above the thermal limits. It should be loaded below the thermal limit, which will act as another constraint on system. Then phase angle between two nodes should not be too large. Okay. If there is a huge or a very large phase angle, then angular stability constraint, which means angular stability will come into picture, which means there will be disturbances, but it should not be too large. When you change that control variable, it should not create a huge or too large angular stability. Okay. Then setting of all the control variables should be within their available range. Means example, generator output should be within the capability curve. When you set, you cannot set that. Okay, so but it should be within the range. Example I have given is generator output should be within the capability curve, which we have drawn in the unit 1. Then constraint of energy supply system is, we have to see also the constraint of energy supply system. Example, water usage in hydro plant. So if there is no inflow at all, so now how you can increase or how you can control the control variable or change the control variable? We have to see that. Then another constraint on turbine and boiler operation may restrict the power output range. Okay, so which means even that turbine or for a steam one, boiler operation has their own constraint. We have to see this all when you change the control variable. These are the system constraint which we have to see, and then the system constraint can be expressed in the mathematical form. Okay, so system constraint can be expressed in mathematical form. Okay, so in general constraint can be, so now what you can see is all these 8 constraints can be classified into 2 types. One is equality constraint and another one is inequality constraint. Okay, equality constraint and inequality constraint. So based on this, so now equality constraint can be expressed by one mathematical equation expression. Okay, here it's not an equation, but it is just an expression. When we do an optimization, we'll derive some mathematical equation. Just now we have written just a function that equality constant can be expressed as g of x comma u equal to 0. Okay, which u is a control variable. There are 9 control variables which can be set by the operator. So we have learned that control variable, there are 9 control variable, and then this 9 control variable can be set by the operator. Example 1.1 per unit voltage, it is a nominal, but you can set to 1.02 based on the generator capability curve. Okay, this is control variable, and then this x. Okay, this x is a auxiliary variable like voltage and phase angle at bus. Okay, so this x is a auxiliary variable like voltage and phase. Okay, and then inequality constant can be expressed in terms of this h mean, okay, by this equation, and then x it is same. Okay, so control variable, okay, sorry, not x is not control variable, auxiliary variable, and a u is a control variable. So in inequality constant, what it will have is it will have a maximum limit and then minimum limit here, h max and then h min. Okay, so now this is just a general expression of equality and inequality constant. So in equality constant, what it will say is just will express that g x of u equal to 0, which means u is a control variable. There are 9 control variable which can be set by the operator, and x is some auxiliary variable like voltage and phase angle. And then inequality constant can be expressed by this equation, and then in inequality constant there will be maximum and minimum. So that's why you might have seen that all frequency maximum plus minus, you might have seen plus it might be 50.5, minimum it can be 49.5 like this, or voltage you might have seen 230 but plus or minus 5%. So you can calculate that and then you can see. So and an example of a equality constant equation are the real and reactive power balance. Okay, so this one we will learn in the uh, optimization. An example of inequality constant is voltage magnitude at the load bus should be within minimum or maximum limit. Okay, so here what you have to know is, so when you express in, so you have to know that it is expressed in terms of equality and inequality constant. And equality constant, you will have g of xu, and then where it will have a control variables and the auxiliary. And then in inequality constant, it will have minimum and maximum value. Okay, so this about the constant on system operation. So now if you know this control variable, system operation, sorry, constraint on system operation, then we have to know what is mean by objective function. So based on this objective, so we have to set the control variable. When you set the control variable, we have to see all this constraint, and then constraint equation will be given by this general expression, and later on we will derive this, and then we will see that. And then when you set this all, it has to meet this objective. Okay, what are the objective functions? Okay, so first what I'm trying to say here is, so now scheduling means we have to set the set point, reference point. When you set the reference point, we have to keep in mind control variables. Then when you control this variable, we have to see that constraint, it should not go beyond that constraint. Why we are setting that all based on this constraint, and then all is to achieve this certain objective function of the transmission system. Okay, so what are the objectives? So now it has been said, okay, so theoretically it has been said that there is no unique way that operator may run a power system. There's no unique way as such you have to run like this. There's no dictation that you have to run the power system in this way or that way. Okay, there's no unique way that an operator may run a power system. So if I am the operator and if I am the owner, I may run in different way. And if you are the operator, you may run in the different way. But when you run in your way, it has to meet certain objectives. that objective is, everybody knows that our objective is to make a profit. So there should be less, okay, less expenditure and more income. Okay, so that objective we have to fulfill. But to fulfill that objective, we can run in different way. Okay, every operator can run in your own way. How to run that? Okay, so but when you run in a different way, we have to fulfill certain control variable, constraint, and then all, right? So this we have to carry out, but there is no unique way where everybody can run the pods system in a definite rule. Okay, there is no definite rule as such we have to run. So now, for example, if 5 generator are to meet a certain load, okay, for certain load, there is 5 generator which can meet the demand, load demand, and there are many ways that can be scheduled to share the load. Okay, there are many ways which we can schedule to share the load. So one system operator may schedule in different way, another operator may schedule in different way, but there are many ways which we can schedule and meet the certain load demand. Okay, so but when you do this, our aim should be is, main aim of a system operator is to achieve a certain objective. So you should not forget this. Okay, so when you schedule in your own way, but there should be a certain objectives. Okay, by approximately setting the control variable and satisfying all constraints. So I want to schedule in one way. Okay, you want to, if you are want to schedule in your own way, but you have to keep in mind that it has to achieve certain objectives. By how we will achieve objective is by setting a control variables. There are 9 control variables, but when you set a control variable, it has to satisfy all the constraint, 8 constraint which we have done. And then this is how we can schedule. But there are 5 generators to meet can meet their load demand, but there are different ways which we can schedule. But when you schedule, we have to know achieve certain objective. But how? By setting the control variable. When you set the control variable, then it has to satisfy the constraint. Okay, so then rather than making a random adjustment, a system operator will attempt to make an optimal setting according to some objective or function. So that objective function is cost. Okay, everybody is concerned about that. So instead of randomly making, okay, so randomly adjusting your, so what you have to do is, okay, so what you have to do is, so then you operator will attempt a optimal setting, okay, according to certain objective. That means cost function, objective function is cost. So which means there should be a less expenditure on when you operate this, and then less expenditure means less losses and the maximum return. Okay, so this cost function is a mathematical function of control and auxiliary variable. Okay, so now what we are saying here is, so there is no unique way which we can run the power system, or operator can run a power system, but there are different ways which we can share the load. But when you do that, we have to keep in mind that it has to achieve a certain objectives. How we will achieve that objective? By setting the control variable, approximately setting the control variable. When you set the control variable, it has to satisfy all the constraints which I have listed, right? Or we have to, it has to satisfy all the constraints. Then how we are setting is generally, okay, so in general we will do optimal setting according to some objective function, that is a cost function. Okay, that cost function means expenditure should be less, income should be more, or less losses, more revenue. That this cost function is a mathematical function of control variable and auxiliary variable, which I have introduce little bit on this here, control variable and auxiliary variable. Okay, so then basic objective function only, but let's see where we start little bit on the optimization problem. Basic optimization problem can be therefore formulated by following equations. So let's say minimize, okay, j x u. What is u and x u now? Okay, so x is the auxiliary control, and then auxiliary variable, and the u is a control variable. And then when you minimize this, j is a function only. Okay, so I have not given g because if I write g here, it will puzzle with your earlier one. So just j is a minimize that x comma u. But when you minimize your expenditure, what you have to do is it has to subject it to, means when you minimize your cost, it has to fulfill this g equal to x comma u. What is g x comma u? Is a equality constraint. Okay, it has to fulfill that, and then also you have to fulfill the inequality constraint. Okay, which means when you are trying to minimize the expenditure or a cost involved, which is represented by jx comma u, it has to fulfill or it has to subject it to gx comma u equal to 0, which is a equality constraint, and then it has to fulfill the inequality constraint. Okay, then only we can optimize. If you're not fulfilling these two, and if you try to optimize, then again, instead of achieving a good quality power, and then instead of achieving a minimum cost, so there will be huge losses. Okay, so then what you have to know is, first I have said in terms of cost only, but common objective function are, first one is scheduling generation to minimize the generation cost. So that means unnecessarily you don't try to generate from all the power plant or the generator. Okay, so means schedule that in early hours to generate. Example, let's say there is 4 generator in morning. Let's say 2 generator is sufficient. Towards the peak load time, another generator can be put on, or 2 generator can be put on. Towards afternoon, sometimes 1 generator might have to shut down. Okay, so which means you have to schedule the generation to minimize the generation cost. One thing. Then another objective, it has to objective function are schedule real and reactive power controls to minimize active power losses. So now you have to schedule that real and reactive power controls. How to control the real and reactive power, when to control the real and reactive power, so that your active power losses will be reduced. Okay, and then another one is just I explain here, schedule generation cost on unit commitment. Decide whether to engage generation unit and for what duration based on cost and prime mover energy supply constraints. So now you have to see that unit commitment is also another common objective function, and decide when generation unit will engage or when you will engage that generation unit. So if there are 4 generation unit, either you have to engage all 4 throughout the day, or only 2 units throughout the day, or only 3 units throughout the day, or in time gap 3 unit, and later on you may have to switch on another unit. Okay, and then for what duration. But when you see that, we have to see on the cost of prime mover and energy supply constraint also, whether there is a discharge is there or not. If there is enough discharge for 4 unit, then you can use, and if it is required, that is known as unit commitment. Okay, so this is how we can fulfill the objective function. And then this all objective function, it says time frame of optimal flow can vary. Okay, so and the unit commitment problem is several days or month. Okay, and then this is how we can schedule. Okay, so however this, okay, so we can say that, okay, so scheduling generation cost and achieve loss minimization can be online and that of the order of an hour. But if you see carefully, all objectively listed above are coupled. Okay, so which means all these 3 are coupled one. Means couple here means interacted. Okay, okay, so all these 3 objective function are coupled. Okay, all objectively stable above are coupled, which means when there is active power loss, it will affect the generation requirement. Means there is huge active power loss, we have to increase the generation, which in turns will affect their schedule and also affect the unit commitment. Example, let's say there is a huge active power loss, then what you have to do is it will affect the generation requirement, right? So there are huge active power loss, then it will affect the generation requirement, which means we have to increase the generation, and which in turn it will affect the schedule. Means, so now if there are two generation which will be sufficient, but there are huge active power losses, then means generation it has affected the generation requirement, then we have to put on another one, another generator, which means it affect the unit commitment. Means here what I'm trying to say is all the objective function, three objective function I have made earlier, is a interrelated. Means if one affect, another one will be affected, and so on. Okay, so that's why I have given. But however, for our simplicity, and we consider that these couplings or interrelated are not very strong, and in order to make the problem traceable, we consider that is not interrelated. But in actual sense, it has been interrelated, but if we consider that active power losses is very less and then all, so then we consider that these are decoupled or not coupled. Okay, and then for example, we can see that in the generation cost minimization problem, we have to keep in mind about the economic dispatch. Okay, economic dispatch. Okay, problem only generator which are online. Okay, and then we have to find out how we can go about this. Okay, so this about the objective function of, okay, power system operation and control. Okay, so here you can see that all, since generation, transmission, distribution and load are not necessarily owned by the same company or entity, and objective function depend on entity which is carrying out the optimization. So now to do an optimization, it is very complex. Okay, that's why most of you find difficulty in optimization. So doing optimization is very, very complex, since why we are saying this generation, transmission, distribution and loads are not necessarily owned by a same entity, which means, example, in Bhutan, generation is owned by DGPC, transmission and distribution by BPC, load individual, right? So which means it is not owned by a single entity, and then this make very complicated to carry out the optimization, because when it require BPC, when they will try to improve, when there is a losses, so it has to depend on BPC, right? And when it will be switch on, switch off, the load will depend upon the individual entity or individual consumer. So that this make a complicated one. But in Bhutan, it is almost okay, because generation, distribution, control is, there is only one operator on generation, fully DGPC, transmission, distribution, BPC, load, we can say that there are different. But if you take one example of India, there are different generation company, right? Government on, private, and then all, right? It depends, all feed to the grid. This is also another. Then there are different transmission and distribution company, Tata company, so on. Okay, so there are different companies. So these all has to be synchronized, and it find very difficult to carry out the optimization. Okay, so but nevertheless, in a system where generation, transmission, and distribution are part of single entity. So if there is single entity, everything has been controlled by one entity. Example, DGPC control generation, transmission, distribution. Then we call it as a vertically integrated, means one company. Okay, utility and system operator will try to minimize cost of the electricity to a consumer. Okay, so this will be much easier. But in a system where not vertically integrated, means generation company is different, transmission company is different, distribution company is different, then it will become a very, very complex. Okay, there are several players, right, involved. Generation will say something, distribution will say another thing, transmission will say another thing. So then what it will happen is we will face problem in the optimization. So this has become a more complex. So don't worry about this. Just now you know that if there is a single entity, it is very easy to carry out the optimization. If there is a multiple players involved there, then optimization will be very complex. Okay, very complex, which we will learn. We can do optimization, which we will learn in 7th semester, and hopefully I will take this module only, and then we shall discuss little bit of mathematical procedure for optimizing function under equality and inequality constraint in next lecture. Okay, so that's all about the today's lecture. And what we have learned is today we have learned about the real and reactive power scheduling, but here we have not done scheduling of real and reactive power, just introduction to real and reactive power scheduling, because to carry out the real and reactive power scheduling we have to know first what is scheduling, then what are the control variables and constraint, and then what is the objective function. So that's why we are scheduling real and reactive power to achieve a certain objective. So then we have said what is mean by scheduling, then control variables. Okay, what are the control variables, then what are the constraint in on a power system operation, and then towards the end we have little bit seen under objective function, we have seen little bit how to carry out the optimization, but little bit further or detail of the optimization we learn in next lecture. Okay, next lecture, with that we will carry out the scheduling of real power and reactive powers. Okay, that's all for today's lecture. And if you have any doubt, okay, so you can ask, or if you don't have doubt, so please wait for a few minutes. So I will try to take attendance again. Okay, so okay, it seems there is some network issue, right? Doji Hassan has come online, then again, some are going off and on. Okay, so I think Karmawangdi is there. Mm. Okay, so that's all from my side. And then just I want to ask one last question. How you are coming online through VLE, or somebody shared the
Through
link?
VLE, sir.
Pardon?
VLE, sir.
Through
VLE?
VLE, sir.
Okay. So because some are complaining that our VLE usage is only around 400, we have 700 student plus, so it's only 400. But when I talk to some of the students, they are saying they are coming via link which their friend has shared. Okay, so but third year most of you are coming via the VLE. Okay, so thank you. If you have any doubt, you can ask. If you have no doubt, then so we'll end here. Our lecture will be ending here. Okay, so thank you for coming online.
Thank you, sir.
Thank you, sir.
Thank you, sir.
I hope you are getting it. Now this optimization and this all are very, when you really do a optimization, it will be a little bit tougher, but the tough portion will be in the next module. Name itself is optimization. Okay, so which means one semester you will learn optimization. Here we will only carry out the uh, preliminary of the optimization. Just you have to know what is meant by optimization, how to carry it out, and then why we are doing. Okay, so that's all for today. Okay, so thank you for coming on.
Thank you, sir.